हाँ तो शुरू हो गया रिकॉर्ड.
Okay, so the conflict. Hmm.
So right now it's just a small, let's say, an small idea ki what was the conflict going on between Newtonian gravity and special relativity.
Hmm.
So the time is when Einstein was trying to formulate general relativity. So he has discovered special relativity, and Einstein was like, ki, okay, now how to extend this concept of special relativity? Because in special relativity, gravity was not included. So Einstein was right now working on ki, okay, what is the, let's say, the mathematics, or what will happen if I think about gravity, but in context of special relativity. So first of the things, so first you have to understand what is like what are the basic things in Newtonian gravity. So like in Newtonian physics, so Newtonian physics like F is equals to ma or v is equals to u plus at. So these are covariant. Covariant means that they do not change their form, because this, if there is a formula F is equals to ma, it would be same in, let's say, if I have xy axis and if I rotate the xy plane along some z axis, so the axis will change, but the formula, this F is equals to ma, will still hold.
Will not change. Huh?
Yeah. So you say that okay, this is invariant. So this is covariant under the three-dimensional orthonormal group of transformation, which is generally the rotation group, because you are rotating around the x-axis. So this,
Hmm.
as you know, that it generally preserves the distance, which is r is equals to x square plus y square plus z square,
Hmm.
apart from the Galilean transformation in space and time. So these are the two equations which we know, that F is equals to g m1 m2 upon r cube. R cube because now I am specifying the distance over here. So this is
Huh.
the unit vector. And then we know the Poisson equation, that if you have some matter of some density, then it will create this potential. So this is the Poisson equation which we do. But here you see that if the, you can see the cursor, right?
Yes, yes.
Yeah.
I forgot the rho is the density
Yeah, rho is the density of the matter, mass upon volume, and phi is the Newtonian potential. So
potential.
this gradient of phi is the force, right? Force is equals to dv by
Yeah.
that thing. So in this equation, if you look into this equation and then you say that, okay, I have some density of matter, I have a ball. But if the density of matter goes to zero, which means rho goes to zero, right? The density goes to zero. It means that this potential, this gravitation potential will also be zero. This is
Yes.
what this equation is telling us. So right now in Newtonian gravity, the idea is that gravity influences or it propagates at some infinite speed, because since rho is getting zero, then phi is also getting zero. This means that if I switch off the sun right now, then I will feel the effect immediately. This is according to Newtonian gravity. And in special relativity, we also learned that the orthonormal group under which these guys are covariant, it was transformed to a Lorentz group. So Lorentz group, remember that there were three boosts in x, y, and z direction, and there was the velocity, the boost, which is the, sorry, boost is an boost is the, like the velocity in the x, y, z direction, and then it includes the orthonormal group, orthogonal group, sorry, which is the rotation group. So,
Hmm.
so similarly, the idea is that okay, if there was Newtonian physics and if something is being preserved under that kind of group, then in special relativity, we know that this guy was always conserved. This distance, the ds square, ds
Yeah.
square equals to c square dd square minus dx square minus dy square minus, this is z, sorry, not s. So
Hmm.
here, what was happening in special relativity, the Galilean transformation was going to a Lorentz transformation. So Galilean transformation, you know, right? X is equals x prime equal to x minus vt or something, that thing. So uh, if I will write, so I will write that this is a Galilean transformation. So x prime goes to some x minus vt,
Hmm. Hmm.
y prime goes to y,
Goes
z prime goes to z,
to Z.
and time was absolute in
Yes.
Galilean. But in Lorentz transformation, we know that x prime goes to gamma x minus vt, where gamma is the Lorentz factor.
Hmm.
Y prime is same, which is y. Z prime is also same. And we know that time is now not absolute, it depends on the frame. So T prime is equals to gamma T minus V x square by
C
T,
square.
I think. Yeah, something. So you know that, so here the transformation is different. So the basic picture was that, okay, when I'm using Newtonian physics, this these transformations are valid. But as and when the velocity of the object increases, then we know that special relativity comes into the picture, and Lorentz transformation is the actual group, which is which would be
Okay.
governing the physics over there. And now the idea is that okay, in Galilean transformation, you have the Newtonian gravity, but how would you incorporate gravity with special relativity? So this is what Einstein was thinking, that
Hmm.
how he will come across it. Okay, and if you take the two equations of the like for gravity, you take this equation and you take this equation, and then you ask that are these equations invariant under Lorentz transformation, which basically means that if I am in one frame and I am doing these calculations, and if I am in another frame, I am moving with some velocity, and if I do these calculations, will I get the same result? But here you can see that equation 1 and 2 are not invariant under Lorentz transformation. So there is something wrong which is happening. So we need to modify the Newtonian's gravitation to make it compatible with special relativity. So these laws of Newtonian gravity has to be modified in order to make it compatible with special relativity. So this is the basic idea of how we are
So
doing.
basically, they are you have to make them in different. I mean, make a general formula so that it is invariant in any frames of reference.
Yeah, exactly. And now let's say that okay, what is the way out? That how we can escape these things. So okay, the first idea is that maybe if I take the Poisson equation, which is this over here. So I know that this the del is the gradient operator, right? Which is del by, I don't know, it was like del x
Rho
square.
H square, yeah.
Yeah,
Hmm.
that thing. Okay, so now if I think about this, so if first idea would be that okay, if I have to make this equation so and so that things are
Del
propagating.
square,
So del square is del by del x square plus del square by del y square. These are the
yeah.
partial derivatives.
Hmm.
Mm, Del z square. So first thing which I can think is that okay, if I have gravity and if it is propagating with the speed of light, let's say for example, then I have to modify this equation, right? Because this means that if an object is vanishing somehow, then I am getting the information after some time. And if I'm saying that okay, gravity is traveling at the speed of light, then I have to modify this equation. So this equation can be sort of modified in terms of Maxwell's equation, which is the D'Alembert equation, which is the box operator, which is this. So
Hmm.
here you can say that okay, if my rho is going to zero, then it will take some time in order for the gravitational potential to go zero. Does this make sense?
If the mass is tending to zero, then it will take some time for the gravitational potential to
Yeah, exactly.
zero.
So this is one way out. So right now, what we are trying to do is we are trying to see that okay, I have this equation, and how can I make it relativistically invariant? So I say that okay, gravity is propagating with the speed of light. I change the left hand side of this equation, so this del becomes the box operator, which is this. And then I say that okay, if a mass is vanishing somewhere, then okay, there would be some time after it, after which the effects are felt. But so here we have gravity moving with the speed of light. But now one has to remember that whenever you are changing the equations should be Lorentz invariant, which means that even if I go to another frame and then I measure this density, this mass density is mass of the object upon volume, right? Volume, if you let's say if you take volume of a cube, so volume would be length into breadth into height. But now if suppose you are there in this frame and you are observing the volume of this cube, and this cube has mass, therefore it has some gravitational potential, and that's why it has some gravity now. And suppose I am over here and I am moving with some velocity. So when I'm moving with some velocity, you know that in the direction of the velocity this length will be contracted, right?
Hmm.
So there will be a gamma term coming over here.
Yeah,
Is this okay?
yeah. I mean,
Yeah. So here you can see the
length
only
contraction.
yeah, length contraction. So here you see that this mass density thing, this is not Lorentz invariant. So this equation again has some problem. So now what you can do is, what one can do is that, okay, maybe I take this as a, maybe I take this right hand side of this equation as some time component of a second rank tensor, so that what if there is some machinery which involves that this also changes relativistically. But then the issue is that this scalar potential which we are dealing with, this becomes a mystery, that what is this in the terms that how is light affected by gravitation. And if you consider the concept of inertial frames, then if you have an object which is experiencing no force, then how will you achieve the state of no force with this equation? So right now the basic idea is that, okay, you will have, I mean, when, so now the basic idea Einstein was having, that okay, if you will have some equation of general relativity, you will have obviously matter at the right hand side and some object, I can put a question mark, and
Mm,
this has to change in such a way that it is relativistically invariant.
mm, mm.
And also one of the major thing is that if you are considering inertial frame, because whenever in physics we deal with, I mean, the very first object is that an object at rest, right? An
Yes.
object at rest has no force.
Mm,
So the question was, Einstein was thinking that how to achieve the state of no force, because the question is that it is possible to shield a piece of matter from other interactions but not from gravitation, because everything attracts.
yes.
So because the
There
equipment
can
which,
never be I
yeah,
mean, a particle which has no force. Just like there's no free particle, right?
yeah, exactly. So Einstein's idea was that if gravitation is some form of a permanent nature thing, then it must be intrinsic to the region, or I mean intrinsic to the region it is located. So he identified this intrinsic property of space-time region with its geometry. So remember that he was trying to modify this equation, which is here. So right now Einstein has reached over here. So
Mm,
this he's saying that okay, there is matter and all, but this matter has to be related to something, and that something should be such that it should incorporate how light is affected by gravitation. It should have a concept of inertial frame, and that exact thing, what Einstein thought was that it is just the space-time geometry.
mm,
And therefore the idea is that okay, in special relativity you discuss flat spacetimes, and when you include matter, that spacetime is curved, and that's how your space-time geometry is related to the matter. So now the idea is to figure out what is this space-time geometry, or what are the mathematical tools required to understand this space-time geometry.
mm.
So now we will begin with this. Now the it starts that we have to learn about curvature.
Okay. Tensors. Mm.
Yeah. So this is visible, right?
Yeah.
Okay, so we remember that in special relativity we had this guy, ds square, right? The space-time interval. It was
Yes.
eta alpha beta, but this eta was all constant, minus one, 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 one. Now
Mm,
we know that because we have moved into the gravity regime, so this eta is no longer a constant, but is a function of the space-time itself. So this is a function of t and x.
mm,
So that's that is like one step how to go there. Mhm. And one of the straightforward generalizations of, let's say, because right now, how do you start? Okay, so first of all, how you define this mathematics in a very proper way is you define something which is called a tangent space. So this is nothing but you can imagine that, so imagine that there is this apple.
okay.
So there is this apple, and I will just call it a manifold M. Why I'm calling it a manifold? Because it can have any shape depending on what I choose. Which means that if there is an apple, then obviously the manifold would be different, right? Which means that this curvature. If you take a orange, it would be different.
Yes.
Or I don't know, if you take a banana, it would be different. So first thing to understand is that there is this manifold, which is the extensive geometry. And now you define a tangent space. Now imagine that you have like you are like very tiny, and you are an ant basically. It's not tiny, but you are an ant and you are walking on this apple.
Surface of the apple.
Yeah.
Okay.
So because you are on the surface and you are two-dimensional human being, you will not notice the curvature of this apple. You will just move
Yeah.
on the surface like this. So
It
on
seems
the,
flat.
yeah, it seems flat for a two-dimensional person. So you can imagine that there is a plane. Okay, so I will just zoom this out. So I will just draw it like this. Okay, so this line I have drawn it horizontally. So what you will imagine is that there is this plane, and when you draw a tangent plane to it, then all the vectors which are coming out will be tangent to it and they will be on this plane. Why this is important? Because right now you are on this flat region, but when you will, suppose you are walking here and then you reach this curved path. So I will draw it here. So now if you draw your tangent plane, there would be some vectors which which would be different. Because I mean the basic idea is that if you have a flat plane, then if you draw, if I mean if you have a flat line and if you draw some plane over there, then all the tangent vectors will be lying in the plane. But when you are at the curved surface, some tangent vectors will be going away from it, and
Mm-hmm.
some will be lying on the surface.
Yeah.
Obviously you have to imagine that we are very close to the apple or something. This is very simple. I mean, if you can also imagine if you have a table. Suppose you have a table, and if I draw a rectangle sheet, I have a point and I draw all these lines. So you can see that all these lines are parallel to the surface, right? Parallel,
Yes.
or let's say they are lying in this surface. But if I have to draw this same plane at the edge, you will see that some tangent lines are coming out, right? It's just that
Yes.
thing.
Mm-hmm.
Okay, so we have that concept defined. So now you want to generate, because till now in Newtonian mechanics and all, and also in special relativity, we had come across three characters. One is scalar, one is vector, and the other guy is the tensor. So tensor was the guy in which we were representing space and time as one entity or something, that thing. So this eta mu nu also, it's a tensor, minus one, minus one or something. So now we have to understand how tensors will help us define the geometry of the space-time. Okay, so tensor is an I do need clear, yeah, okay, here. Okay, so I'm right now here. So tensor is an object that is invariant under a change of coordinates. Plus the components change in a very special way. Because now what you want is that, again, if you imagine the apple, or if you imagine an orange. So now the idea is that if you are an ant and if you are moving on an apple or if you are moving on an orange, then it should not depend whether you are moving on an orange or an apple. The notion of distance should be the same, right? If you are moving 5 meters over here, then you should move 5 meters over here. The notion of distance or the notion of velocity or the notion of any physical quantity should be independent of whatever m you are taking, whatever manifold you are taking.
Yeah. I
Now,
mean, in the sense, you walk. It's just like you walk on one plane or another plane. It should be the same.
yeah, because there should be some common notion of distance, right? That if you have moved 5 meters on this, you should have moved 5 meters on this.
Mm-hmm.
So tensor is an object which is invariant under a change of coordinates. Because eventually what is happening, that you can represent this apple with some coordinate, right? You can write x and y axis. And
Mm.
similarly, you will have an orange with some x prime and some y prime. So you
Mm.
can see that when you are moving in an apple, you have one coordinate system. When you are moving in an orange, you have another coordinate system. But the notion of distance is same, right? Distance means the length of something.
Yeah.
So these tensors are the objects that are invariant under a change of coordinate system.
Mm.
So now imagine that you have a you have a plain paper or something. Yeah, you have a two-dimensional paper, and I draw a vector v, and I just shift the base of this vector in this direction. So I will write the change as dv by dx. This means that how much my vector is changing, which makes sense that this vector would be here, this vector would be here. So how much it is changing. Now imagine the same thing on a sphere. So on a sphere, if at one point you draw the you draw the vector like this, and now if you go to another point, you can see that something is changing. So I will draw it again over here. If you have a flat surface or a plane surface, you draw a vector. If you move it around, it will still be in this direction, right? I mean, if you're changing the angle and all, that's different. But if I don't change the angle and all, and if I just displace it over here, this tangent will be the same, right?
Yeah. Mm.
But if on a sphere, if you take a vector and if you take it in this direction, your tangent vector changes. This is a property of curved spacetime. So now the idea is that okay, since you had this derivative operator in flat spacetime, what would be the derivative operator in a curved spacetime? So this is the basic idea that when you are going from flat to curved spacetime, you meet this guy, which I denote by capital D, which is the covariant derivative. And now we have to understand how these covariant derivatives act on vectors. Because right now what you are doing is if you have flat space-time, you have some vector, you change that vector. If you understand this change, you can calculate the velocity of the object, you can calculate the momentum of the object, and so on and so forth. But now you have a curved surface. So in curved surface, when you are moving from one point to other, you need the notion of this derivative in order to understand or define how things are changing. So this is
Okay.
the
So
basic idea, like how
covariant
you.
covariant derivative is only, is it for any curved surfaces, right?
Yeah, yeah, it's for curved surfaces. And when you are in flat surfaces, you will see that covariant derivative is defined like this. And when you are in a flat surface, this guy goes to zero, and you have the same derivative as like this. So this dv by dx can be written as some del mu of v. Because see here right now I am in two dimension, but if I suppose I write this as dv by dx alpha, then it would mean that this is dv by dx0 plus dv by dx1 plus. So because there is a repeated index over here. I mean, this
Mm.
I'm giving an example of two dimension, but you have to imagine that you are in flat four dimension and now you are going to a curved space time. So we'll now discuss more on this. Okay, so now we come to space time and the the coordinate system. So I will define it once again. So you define, I think this we did in last class, but anyways, it's fine. So generally, when I write x1, it is the x coordinate, x2 is the y coordinate, x3 is the z coordinate, and x4 is the
The time.
ct. Or you can define it vice versa, that x0 can be the time coordinate. This is just the time coordinate. So ds square is eta alpha beta dx alpha dx beta, where dx alpha, it denotes the infinitesimal coordinate change between two neighboring points, p, which is at xi, to p prime, which is at xi plus dxi.
Let's
And this is simple because in flat space-time, which means that you are in Minkowskian space-time, you have the eta ab as a constant matrix. So you can calculate this. But now you go from flat space-time to curved space-time. So you have g alpha beta. And now the question is that, okay, if I'm going from some point uh, x alpha to some point x alpha prime, how will things change? So we have to figure out like how these guys will change.
You have G alpha beta spacetime and assume it's twice differentiable.
Mm, I coordinate, yeah. Okay, so if you have to, let's say, let's look at this equation. So, okay, I have dx alpha or something. Wait,
It's क्या हुआ?
ठीक आ रहा था.
Okay.
Okay, so you have dx prime alpha. So I'm in the prime coordinate. This prime coordinate is nothing but the changes in the prime coordinate with respect to like the changes happening over there, right? This x gamma could be, I don't know, in x direction or y direction or that kind of thing.
Mm-hmm.
And so this is like going from prime coordinate to unprime coordinate. You can see that I have dx over here. Similarly, you can have dx gamma and you are going to dx prime. So remember in special relativity, we were going from x to x prime or x prime to x.
It's
Now
yes.
there are these similar transformations which are there for when you're going from one frame to the other. The only difference is here this other frame was moving in some velocity v, but now
Yeah.
here the other frame can be doing anything because it's a very general definition.
Mm.
And now the idea is that we need quantity. So there are quantities which are related to the intrinsic property of space-time. By that, what we mean is that those quantities should not depend on any special coordinate system. And now we have to find out that, okay, what are those quantities in terms of scalars, vectors, and tensors. Okay, so first let's look at the scalar. So scalars, we know that these are quantities which do not change magnitude under a coordinate transformation. So suppose you have a scalar which is phi and it is defined by the position xi, and you know that this xi is going to some prime frame. I can write it as x prime. There must be some transformation and you can transform it as phi prime. So you have a scalar function phi and you go to another coordinate system with phi prime, and then you can sort of define it like this. And ds square, let's take an example that ds square is a scalar and it remains unchanged under the coordinate transformation. So we know that ds square in one frame is g alpha beta dx alpha dx beta. This we are saying that it is the same in both the frames. So this would be equal to g alpha beta prime dx alpha prime and dx beta prime. So this is which we are asserting because scalars are such quantities. So if we use, okay, so first of all we need the expressions for these guys, dx alpha and dx beta. This we had already defined over here, which are like this. So is it still visible to you?
Yeah, yeah.
Yeah, because I'll just use these equations here. So where I'm focusing on this equation, g alpha beta dx alpha dx beta. So I go over here. So this is g alpha beta. Dx alpha can be written as, you can, so let's say I take this equation. So I know that dx, indices, I mean, Greek indices, you can use any. So let me use some mu index over here. So dx mu, I'm writing as dx gamma, which is the same frame. So dx prime. Oh, wait a second. Hold on. Yeah, let's do it again. Okay, so I have this equation which is g alpha beta dx alpha and dx beta, and I want to see how things are changing. So the idea is that you just put these values. Similarly, you put these values and then you see how things are changing. One can do this calculation and you will come across that the g alpha, I mean, the g without a prime is related to the g with prime, via such a transformation. So this is like the basic result of this, let's say, this
You
calculation.
get metric functions of new coordinates.
Yeah.
Wait, okay, anyway.
It's just that you are in one coordinate system and you need the metric function of the another coordinate system. So this is the old coordinate system, g alpha beta, and this is the new coordinate system, g prime alpha beta prime. And how are these old and new coordinates related? It's via this. This is just a simple relation between them. So now, since we have done scalars, hmm, so now we move on to vectors. Okay, so the laws of physics are described by means of differential equations, which relate the change of a physical quantity with respect to space and time. So now we want to know how these vectors are being transformed with space-time coordinates. So earlier we saw that if you have a scalar function, which is going from one coordinate to another coordinate, then the formula is above how things are changing. And now you have vectors. So vectors are generally guys with single indexes. This represents your the x component of the vector, the y component of the vector, the z component of the vector. And now the question is that, okay, I have a vector, and now if I go from one coordinate to another coordinate, how will things look like?
Hmm.
So this is what we will figure out here. Okay, so first of all, how you define the change of a vector is by this. So del ai upon del xk, this is represented by a comma.
Hmm.
You can see this, right? The comma.
Yeah. Hmm.
So this is how you define a normal derivative of a vector. And now the same thing. So you have this derivative in some coordinate system, and now you are going to another coordinate system. So one can like do this uh, little bit of calculations, and you will see that you will get one quantity which which changes like a tensor. This is due to the previous equation which we had, and then there is another quantity which do not change like a tensor. So the basic idea here is that when you take a vector and when you are going from one coordinate to another coordinate, then for right now, it seems that it does not transform like a vector. And the spoiler alert is because there is this quantity here, you are only using the partial derivative. It's only when you will use the covariant derivative, you will see that a vector is perfectly transformed. So this is just showing that if you just take a partial derivative of a vector, it does not transforms like a tensor. And we know that tensor is a quantity which is independent of the coordinate system. So that is what we need. Because right now, whatever we are doing is that, okay, you have a scalar and you have a vector, right?
Hmm.
And why are we focusing on this? Because we know that all these gravity and special relativity and all, they have either vectors or they have a quantity which is a scalar, right? And now you
Yeah.
want to understand that if I'm going from one coordinate to another coordinate, but now it's a curved space-time, not just flat space-time. How will these guys change? So we are trying to understand this, and in this exercise, what it is being told that, okay, if you are going from one coordinate to another coordinate, and if you are just using these partial derivatives, which is generally used to imply differentiation, you see that these vectors cannot transform when you are using partial derivatives. And okay, so now we come across another notion which is called parallel transport. So it's the basic is the same, that if you are in a flat space-time, you see that if you have a flat space-time and if you have a vector A and if you transport it, then it is very simple, right? Because it lies in the same tangent plane, because you will draw a tangent plane, all the tangents are the same. But here you see that if you have a curved space-time, then you want to figure out that you know how this vector is changing. So this is some some curved, so you can imagine that this is this part of the apple, and now you want to see that, okay, when I'm going from point P to point Q, And if I have a vector at point P, how will it be changed when I go to vector at point Q? So the idea is to figure out the geometry of what is happening. So how to transport a vector AI from P to Q? So uh, there is one mathematical tool which we will need is, there is something which handles the component of the vector. So I'll tell you what that is. So this is a vector A. I generally write it as, I mean, in two dimension, I can write it as AX x cap plus AY y cap. This, you know, that this is the scalar part and this is the unit vector, right? In
Yes.
the x direction, on the y direction. So now if the coordinate systems are changing, so I have x and y. If my these guys are changing, the coordinate system itself is changing, then there is some mathematics which involves that how these guys are changing, how the components of a vector are changing. So these components of a vector, they generally change with the help of Christoffel symbols, which are these
Mm-hmm.
gammas. I'll just zoom in a bit because now it will start. Okay. So now what I have said, that the components of the vectors are changing with the help of Christoffel symbols, these gammas. And I forgot to say this, that when you are writing these indexes at the top, they are known as contravariant. And when you
And
write it at the bottom, you
right.
write it as covariant. And there is just that gammas will always transform the component, but in a different manner. Different manner being only that plus or minus will come. Otherwise, if you are changing the components of a vector from one coordinate to another, your Christoffel symbols will help you. And now we come up to the main notion, which is the covariant differentiation. So using the notion of parallel transport, this thing, one can define a, a covariant differentiation like this. So covariant differentiation is generally written as some nabla operator with an index. So this is this, which implies that there is a, which are also written as a semicolon. So del L of, suppose AI, this is denoted by a semicolon. And what this involves, it involves first the normal partial derivative of a vector plus how the components are changing. How the components are changing is the Christoffel symbols. So this is how it is changing. And
That's
similarly,
a short form, is it? Okay.
that is the,
No, AI semicolon L.
yeah, yeah, this is just to, how to say,
Short form.
yeah,
Okay.
it's a short form. Because remember that del by del x of some a vector with respect to k component, I just write it as ai comma k,
Hmm.
right? And now this is a covariant derivative. So you have a semicolon. It means that you take the partial derivative plus there is another term which involves Christoffel symbols.
Mm-hmm.
So, and similarly, just to remember that this is the contravariant component. So this
Yes.
covariant derivative acts on a contravariant component with a plus sign, and it acts on the covariant component with a minus sign.
Mm-hmm.
So till now, what we have done, that okay, so you have a vector AI. This will change in a covariant manner when you have the idea of a covariant derivative, which is this semicolon k, or you can write it as nabla k AI. Okay. So now, okay, now, okay, so now the tensors is happening. So what are we doing? Why are we doing this? So we are doing this because we want to understand that what is a straight line in Euclidean space. Euclidean space is the normal x, y, z thing which are like perpendicular to each other. So there we know that it is known as a geodesic. So now we need to generalize this definition also. What is the definition of straight line? But since we are in curved space-time, we need the definition in a non-Euclidean space-time, non-Euclidean geometry. So there are two definitions of a straight line. Its direction does not change as we move along it. And second thing is the shortest distance between, it is the shortest distance given between any 2 points. So this is the definition which we have of a straight line, and this is what we'll try to extend. So imagine that you have a curve like this, which is parameterized by lambda, which means that okay, x1 of lambda, x2 of lambda, or something, and you have a point P, and there is a vector, tangent vector u coming out of it. So now I want to know that how this vector is moving on this curve. So since it is it is moving along this curve only, I can write it as a derivative of that parameter. So this is dxi by d lambda. So now the condition holds that this curve should not change its direction as we move along it, means that the rate of change of u along u is zero, which means that this vector is not itself changing.
Rate of change of view along you.
Okay, so let's do it once more. So okay, so I have a curve rho. I define it as rho, and it is parameterized by lambda. So I have xi of a rho. Okay, so now at point P, I draw a tangent vector u, and now I'm requiring that this rho should not change the direction, which I mean that okay, so now suppose I'm drawing rho, it does not change its direction. You can see what it means. That it means that it should go in a straight line.
Yes.
So what this will mean for the tangent vector. So what this means for a tangent vector is that its covariant derivative should be zero, because we saw that tangent vector is a vector, right? And when vectors are changing, one needs to take care of how the vector is changing. That the covariant derivative should be zero.
If,
So you have,
if
yeah. So one has to take the covariant derivative of this guy, ui. So remember that when we were taking the covariant derivative, the first thing was you just do the derivative with respect to the normal, with respect to the derivative which is there, right?
hmm,
So I'll just,
covariant
one
derivative
second. Let's see the
is
definition.
going up.
Yeah, this thing. Yeah, so keep this thing in mind that the covariant derivative is nothing but the partial derivative
Hmm.
plus the Christoffel symbol, right? And now what I'm doing is I have del, I have a lambda because I'm changing around lambda, and I have ui. And since I want this curve rho to be a straight line, so I'm saying that okay, this del ui would be zero. This is my condition of a straight line in a curved spacetime. Okay. So now I just expand this. So I have the covariant derivative of a vector. This ui is a vector, right? Just ai.
Mm-hmm.
So this is del lambda of, this is the ui, which is dxi
By d lambda.
d lambda. Okay, so I have this vector. So if I expand this, I know that first thing would be just the partial derivative with respect to x lambda, which is this, right? xl. So here it would be just,
Dou x square. Shouldn't it be dou square x by dou?
yeah. I'm just expanding that step. So this is what we are getting, right?
Hmm.
Yeah. I mean, this is what you were saying, right? Dou x square by blah, blah, blah. And now I will have obviously the Christoffel term, index and all we can maybe check later. And now what we are having, we have ak is obviously this, which is dxi by d lambda. So we will get this kind of term where first will be a double derivative and then you will have a lambda kind of something. This is clear, right? How we
You
are
wrote,
deriving it.
but you wrote, okay, anyway, you wrote dou x k by dou lambda.
I have okay, I cannot go back on this.
No, 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 no. It's you wrote, not now. I mean, on your page, you have written. it to be dx power k by d lambda.
Yeah, I mean indexes can be, you can change the indexes, it's fine.
Hmm.
Because indexes are just numbers. I mean xi is, I don't know, same as xk
Okay.
for right now, obviously, because yeah. So here I'm getting I'm just checking that how this extra thing is coming. You can see that there is one more term coming, right?
Yes, yes.
Yeah,
dx
this though we got because it is the vector itself. And
you wrote dx k by d lambda dx power l by d lambda, but there is nothing for I. But anyway, it's there in lambda I. Contravariant index I.
that is there, but I'm just thinking how this extra term is coming. Because remember, I mean, if I'm taking a derivative of this, the covariant derivative, so obviously I took a covariant derivative of this, right? Dxi by d lambda. So the first thing is nothing but a partial derivative. So this is dx square xi by d lambda square, plus then there is the gamma term. Then there is obviously this term over here. So there would be a, the I index obviously goes here. Okay, that I don't care. But how is d lambda plus there is another term which is appearing here. Can you see this? There's this extra term also coming.
Yes, it's coming.
Yeah, but I forgot why it is coming here.
No, because in the subscript you have sorry, not subscript. In the covariant part of lambda, you have written KL, no?
I mean this k and l,
Hmm.
but why there are two derivatives? I mean because if I will expand this, I will only get one, right? According to what we have defined. See, this thing which we are defining over here, this is del of ai, right?
Yeah, you're getting two.
Yeah, because
A
here,
AK, AK.
yeah, this is
Yeah.
ak. So here ak is this guy.
Hmm.
So I was just thinking how did the other guy came,
Maybe
and
it's the
the
now.
other guy actually, I mean, it comes, other guy is there. Wait a second, this is del xi of, this is ak. Uh,
Sample that gammas tend to zero.
because I'm pretty sure that these guys come because the, how to say, the indexes of a system are always, sort of satisfied, because this is what, this is like some derivative or something. This I am deriving it. So on the right hand side I have a one index operator ui.
Hmm.
This index is generally not counted. So here I see that I have a I. This is correct. This k and l, this k and l, they are repeated index. So I can chuck them out, and I have an I index here. So that's why this whole equation is correct.
Yeah. I mean, if you by tensor form, it seems right, but
Yeah, but I have to see how. Anyways, let's move on for a moment. But I will tell you later why this is coming. But this equation comes like this. And now you see that if you are in flat space time, these gammas they go to zero. And when
hmm.
this gamma goes to zero, you have just this thing dx square xi upon d lambda square. And you remember the Newton's equation, right? Which is F equal to ma.
Yeah.
So this m was nothing but dx square by dt square, right?
Yes.
So now if the force is on an object is zero, it means that there is no acceleration, right?
Hmm.
So if an force of an object is zero, it means that if an object is moving in a straight line and if there is no force, it will continue to move on a straight line. So here
Hmm.
you see that you are getting that kind of thing. So I mean, this is one of the analogies that in flat space time, if a body is moving in a straight line, it will always move in straight line, which is this. So this was the idea to get like this thing.
So unless and until there's any
Huh.
potential.
Yeah. So actually, what gravity does is that because in flat space time everything is, I mean, there is no gammas and also it is zero, it is fine. But if you have a curved space time, okay, so now you have a curved space time, there are these gammas. So you can see that if a body is moving, it will have this kind of force, right? And that's how, if you have a sun and if it has bent the space time, and this is what people mean, that the space-time has bent, it means that there is some gamma. And now you can see that if a particle wants to move in a straight line, it will move in a straight line, but it will move in a geodesic, like this,
Hmm.
governed by this equation. So this is how, where the bending of space-time is coming. So if you have a flat space-time, the gamma is zero and the particle will move on a straight line. But if you have an object, it will bend the space-time, there will be these gammas, and then you will have a bending effect. So that's how the earth and everything goes around the sun and all.
Hmm. Okay. Difference. Okay. No.
Difference between one and,
Yeah, you're telling the same thing.
oh yeah, so okay. Mhm. And I'm telling the same thing, that now if you have a curved space time, let's say I have a sphere, and if I have two paths, I start from one over here and I go here and then I start from other here. So this, I mean, this is a spherical geometry because I have taken a spherical example. So this deviation angle, okay, first focus over here. So you know that generally this deviation angle is v is equal to phi times this vector, right?
Hmm.
This we used to do in a circle or something when it was flat space, when it was flat. I mean, when you consider a circle, your v is equal to this. So
Hmm.
here, if you take the double derivative with respect to u, this distance, you will get zero, right?
Hmm.
But when you do the same thing in a sphere, so in this sphere, it's the same thing. In the sphere also, this deviation between P and Q, which is represented by V, is almost equal to phi times sine of U. This is when you do this calculation in a sphere. And now you see that the double derivative is not zero, right?
Hmm.
So here the difference between the first and second is how curved spacetime differs from a flat spacetime. This is what is happening. So if you have a circle on a flat space-time, and if you want to know the how distance between is changing between 2 points, you get this kind of formula. If you do the double differentiation, you get it as zero. But if you do the same calculation in a sphere, because sphere is intrinsically curved, I mean it's not visible here in the paper, but when you will do the calculation, you will see that the double derivative is not zero. So this is telling you something about the space-time, that the second derivatives will not be zero.
Yeah, it is. Yeah.
Yeah, and now the important thing comes, that these gammas are actually n- because I have defined gammas, but I have not told you what these are. These gammas are the derivatives of the space-time metric, the g alpha betas. This is how they are defined. So you can see these are the first derivatives. This is the space-time, and this is the first derivative. Correct?
Hmm.
So these are, so in flat space-time, these are zero. But now we need, let's say, a condition which says that the second derivative, maybe the information about curvature is hidden in the second derivative of these guys. So I will have a second derivative d square alpha of g alpha beta, and now we need to find these second derivative guys. So first of all, there is a lemma which just says that if you have the covariant derivative, so if I take, let's say I have the covariant derivative del I take two covariant derivative. First I take with respect to L, then I take with respect to, oh sorry, first I take with respect to K, then I take with respect to L. I do the same thing, but now I do it in reverse. Del L of del AI. Now for a moment, let's go back and see what happens for a partial derivative. So if you have a partial derivative, del x del y of a, you know that if I subtract it by del y of del y del a of del x, so what will this give me if I have a partial derivative?
So this will be dou square
No, no,
a
so
by dou x dou y
yeah, so
minus dou
this will
square
be,
a by, oh, it will be, yeah,
it will be,
0.
it will be zero, yeah. So because this is happening when you are taking partial derivatives, but remember that these covariant derivatives, they have this gamma guy inside them. So this is basically not zero, but it is given by this guy over here, this big RIMLK or this thing.
Oh my god, okay, lemma. Hmm.
Yeah, yeah. So this is a lemma, and now we have to understand why this is important, why this guy is important. So first of all, we had this guy G alpha beta, which is the space-time geometry. This we did. Then we had the gammas, which is nothing but the first derivatives of the space-time metric. And now we need this guy R, which is a function of these gammas. I'll tell you what it is. For now, just keep them in mind. So suppose you have a bundle of geodesics, like bundle of freely falling paths, which is like
Hmm.
some path. And now you want to know that how the path between two geodesics is changing. So I focus on this del Vi, and it turns out that how this path is changing is told by the geodesic deviation equation. This is a form of it, and this again has this this R guy. I will just call it for the moment the R guy. And now the funny thing is here is that if this R guy is zero, then these curved geodesics are nothing but freely falling particles. In a freely falling particle, you know that there is no force, right? Because they are falling on a straight line.
Hmm.
So when this curvature part is zero, you can say that the particles are falling a straight line. So the vanishing of this guy, R alpha beta or something, implies that you are in a flat space time. And now I will correct one thing because I told you something wrong. Yeah. So remember that initially I said that when the gammas are zero, you are in flat space time, right? This is what I was telling.
Yes.
Yeah, but this is wrong. Why? Because suppose you take a cylinder, okay? This cylinder will have a space-time geometry which is given by dr square plus blah 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 something something. So this dx square is your g alpha beta. You can calculate your gammas for it. Okay, you will calculate the gamma by, I don't know, the formula is something like this. You can calculate it. You will see that the gammas are not equal to zero. So for a cylinder, these Christoffel symbols are not zero, but still this cylinder is flat. Why? Because if you take a sheet of paper and if you join these two sides, what you will get?
A cylinder.
You will get a cylinder. So this gammas will not be equal to zero, but if you calculate this guy R, which is a function of gamma, then this this will give you 0. So all this mess I'm writing is what I wanted to tell and correct myself is that when the gammas are 0, you cannot be sure that the space time is curved and all. It's only when this R guy, which is actually the Riemannian curvature is 0, then only you can say that space time is flat. So when I was giving you this example that okay, if there is a flat space-time and an object is moving in a straight line, it will continue to move in a straight line. This is true in flat space-time. But when you have curved space-time, it is the Riemannian curvature which is important, which will
Yeah.
define how the path of the particle is around the sun or around a massive object. And now let's just see what this huge guy looks like. So this R, if one does the derivation, is this big thing over here.
Wow. Okay.
And so, yeah, now you can see that first of all, these gammas were the derivatives of the G alpha beta. And here you can see that I have written a comma, right? So this
Yes.
means that there is a derivative again, which means that there is a derivative again. And this is just analogous to this thing which we were doing over here. You can see over here that the double derivative is not equal to 0 means that something is curved, intrinsically curved. So this is the basic. So if you do the same example, so suppose you take a sphere. A sphere will have a metric. ds square is equals to dr square plus blah blah blah. You will have the g alpha beta. You can calculate the gammas. They will not be equal to 0. With gammas, you can calculate the r. And when you will calculate the r, it will not be 0. So this tells you that your sphere is curved or your space-time is curved. And why we are doing all this is with this guy. Oh, sorry. You can see the screen, right?
Yes.
Yeah. So with this 4-index guy, first of all, this is 4-index. So this is RIMLK. With this 4-index guy, you can form a 2-index guy. You can just compress on the first or the third index. You will get a 2-index guy, which is known as Ricci tensor. And now when Einstein was working on this, he wanted to come with an equation. So remember that on the left hand side we had the tik. So he was trying to find a quantity on the left hand side which would be invariant. So this is the quantity which is invariant. So this is
Mm.
rkl minus half rk. These kl are, I should have written Greek indices because initially I had said that I, K, and L go from 1 to 3, but no, here they go from 0, 1, 2, 3, which has the time and the space component. Okay, just keep this in mind. So with this Riemann curvature, you can form a Ricci tensor and a Ricci scalar. And with
Mm.
the Ricci scalar and Ricci tensor, you can define something which is called the Einstein tensor. And this is the thing which will go over here. Where is it? I forgot where is it. Oh, it's here. Sorry. You can see this page, right?
Yeah.
Yeah. So we were saying that we need something on the left hand side in order for it to be relativistically invariant. But now we
Mm.
also need it to be covariant, which means that it should not be coordinate dependent. So this we achieved by defining a quantity which is sort of coordinate independent, and that is uh, the Einstein tensor. So finally, your equations are like this: g mu nu equal to 8 pi.
8
8 pi
by
is a constant, t mu nu.
10.
So you have the sun. The sun will have some t mu nu. This t mu nu will curve the space-time around it. When the space-time is curved, and why the space-time is curved? Because a Riemannian guy comes into the picture, and this Riemannian guy goes into the left-hand side of the equation.
Yeah, that is RKL
Yeah,
minus.
that is RKL minus. So this is like a four index operator, alpha, beta, gamma, delta. With this, you can form a two index operator, which can be alpha, beta, and a Ricci scalar. Why scalar? Because it has no index. And with these two guys, you can form the Einstein tensor. So on left hand side, in the end, you achieved a quantity which is representing the curvature of an object, and
Okay.
that curvature is related to the matter.
So no, wait. Now here, re- the remaining tensor and Ricky tensor are related. Yes, they are
Hmm.
related by RIKLI. So you take this vanishing of RI. I'm sorry, I index. You can
So you
Ricky
have the Riemann tensor, which is a four index operator. If you contract on the two indices, you get a Ricci tensor.
hmm,
If you further contract on the two indices, what you will get is a Ricci scalar. And
yeah.
with Ricci scalar and Ricci tensor, you form the Einstein tensor.
Okay.
And just to remember how these things are related, so this is the space-time metric, which we did was G alpha beta dx alpha dx
DX alpha,
beta,
DX
right?
beta.
So this, if I write it for a for a spherical for a sphere, which I denote by S2, so this would be dr square plus r square d theta square plus r square
Science
sine
square
square theta d
5.
phi square. This is very simple. I mean, this is simple in the terms that I can write it in form of a matrix. So I can write that my G alpha beta is, I know that there is only RR term, theta theta and phi phi. So I will have 1 r square sine square theta. Okay.
Hmm.
And now what I can do with this G alpha beta, I can calculate. So I have not given a formula of gamma. So let me write it over here. So these gamma I, jk, the Christoffel symbols, they are defined as half. Uh, I'll miss the indices, but anyways, so I will write it. Wait a second. Let me just try to write it correctly so that I don't give you the wrong. So, or always the indexes should balance on both the sides. So first
Hmm.
of all, there is a inverse of the metric. Oh yeah, let me write once
So
again.
it will be G
Yeah,
H
so
G
first of
H.
all, this whatever I have written is a covariant form, right? These alpha, beta are in the lower index, okay? And now what I'm writing over here is would be in the contravariant form. So I will
Yeah.
have an index I over here. I will take a dummy index alpha. Why alpha? I'll tell you in a moment. So I will have
I think it shouldn't be I. It should be J.
no. I'll tell you why it is that thing. So this will be first. It would be alpha j with respect to k. Then it would be del g alpha would still be there. There would be a k. Then there would be a j. And I'm just writing. I'll tell you why I'm writing all these terms. And now, one second. I always forget this term. Yeah. So right now, just focus on the orange term which I'm writing. Okay. Then there is a minus sign. I have a del. I have a g. This time it would be respect to the dummy index alpha, and now it will be j and k. Okay. Okay. And now why this is correct is see because alpha and alpha are dummy index. Okay. They will contract. Now you see that on the lower position you have k and j. So you
Yeah.
have k and j, and on top you have I.
Hmm.
Let's look at the second term. On second term, you have alpha over here. These are dummy indexes. They will be contracted. So on the lower index, you have j, lower index, you have k, upper index, you have I. This is correct. Here also, this alpha is a dummy index. This alpha is a dummy index. J and k are lower index and I is the upper index. So this is how you get the gamma. So you see that gammas are the first derivatives of the metric tensor G alpha beta. Once you get the gamma, you can get the R. R is over here. You can you see this term?
Yes, yes.
Yeah. So this is the R. So now what? Okay, let's just go back. So you have uh, yeah, you have a space-time metric ds square is equals to G lower alpha beta. If I take the sphere, I have dr square plus r square d theta square plus r square sine square theta d phi square. I have the G alpha beta. What I can do with G alpha beta, I can take an inverse metric like this. I can define my Christoffel symbols. Once I have defined my Christoffel symbols, I can define the Riemannian curvature, and hence I can define the Einstein curvature. So this would represent. So what this will do is that if you have if you want to know that how a spherical body will curve the space time,
Obvious. Mm.
you will get it in terms of like this with these equations.
So some would be the amount of curvature would be given by Riemannian, and then the matter would be
Yeah.
what is
So
the
but,
T
I
nu,
mean, first of all,
T mu nu.
yeah, T mu nu would be, I don't know, anything which you want. And now the important thing is stop share. Where is the wait a second. Where is Mhm. And now we come to the astrophysics part after this long mathematics. So suppose you have a massive body of mass m and you want to know how the space-time is curved. So this is a spherically massive object m. So this will represent to a particular ds square. So in astrophysics situation, what you have is dx square is minus 1 minus 2gm by r dt square, and I will tell you why this is so. 1 minus 2gm by r inverse dr square plus r square d theta square plus r square sine square theta d phi square. So whatever we did till now was just a spherical object. So right now, what this is a vacuum solution of the Einstein field equation. This whole thing, which means if I'm writing vacuum, it means that my G mu nu is equal to zero. But what this actually represents is that if you have a massive object of m, it will bend the space-time like this, and the space-time is represented by this metric, which is called the Schwarzschild metric. So Schwarzschild metric is a vacuum solution representing spherical distribution of mass. So this is what you have. And now if you want to study that, okay, there is this space, I mean, there is this mass which is bending, and if there is another gas, let's say some gas. So this gas will have some T mu nu, and now you will put that T mu nu over here, and then you will solve whatever equations of motion you need. But, is this clear?
Yes, yes. Uh, I mean, it will go into the the formula which you wrote, no, previously.
Yeah, and now the question is that how, I mean, just one small thing is how do you get this metric? How do you know whether something is an exact solution or not, right? So
Hmm.
you can write ds square is, I don't know, some e alpha dt square,
Hmm.
I don't know, some e beta dx square or something. And initially you assume that, I assume that this is a solution of Einstein equations, which means that when I will plug this into the Einstein equation and when I will calculate the G mu nu, and
Hmm.
let's say I'm saying that this is a vacuum solution, it will give me zero. So now when you know this is a vacuum solution, you will get some constraints on how these
On beta.
parameters are. And when, so let's say if you are solving a spherically symmetric solution, these guys will be nothing but the quantities which I had written, 2 gm by r square and all. So you will
mm,
come to the metric which is majorly used is the Schwarzschild metric. So what does
mm,
Schwarzschild metric represent? It represents a spacetime generated by a spherically symmetric object of mass m. This is the m. And why this is important is that once you go very far away, far away from the object, you return to flat spacetime. How is
yeah. What when you go far away from the source, like for example the black hole, you
Yeah, you will generally have a flat spacetime. Like very far away from the source, you have, because that's how your general relativity should connect to, how to say, the flat spacetime.
yes, yes, there'll be no much
Yeah,
curvature,
yeah,
but
you can see that over here also. So what I wrote was 2 gm by something r. I wrote dt square, and then I had a 1 minus 2 gm by r inverse, right? So when you are very far from the source, so this is your source, this is your space time, and suppose you are over here, this is r, right? So when
mm,
r tends to infinity, this term will go to 0 because this is 1 by infinity, this is 0. This
mm,
term also goes to 0. So you can see that you are getting dt square plus dx square plus dy square and all that thing, right? That is the flat space time. This was the flat space time. Dt square plus, I mean, there was a minus sign over here, so this is minus.
yeah, dy square plus
Mhm.
dz
So very
square.
far from a source, you return to the flat space time.
Yeah, you also spoke this in one of the noise. Yeah.
Yeah, so I mean, this is the basic idea of the mathematics involved. That initially you have a space time, then you see that okay, a space time is generally a curved space time. Then how do you understand this? So the mathematics required is the this tensors. So these tensors are these objects which helps you find out these quantities which are invariant under coordinate transformation. So this is how Einstein discovered the Einstein equation, and then Schwarzschild came up with the solution, dx, the one which we were seeing. Then Roy Kerr came up with the solution of a rotating black hole.
Yeah. Mm.
And I think apart from Kerr's solution of the black hole and the Friedman, Lemaitre, Robertson, Walker, there are no more physically
Observable.
there are no more physically observable, or let's say physically relevant solutions of Einstein field equation, because in the end all are bunch of differential equations, right? You can
Mm.
have thousands of solutions, and there are thousands of exact solutions. So this is what Sebastian does, but majority of them don't have astrophysics or observational aspect, because even if you want to solve a two body problem via general relativity, it is like, I don't know, it's like breaking something with a hammer while you can just drop it. Which means that if you use Newtonian gravity to solve two body problem, it's easier rather than using this general relativity. But if you study gravitational waves and all that, then you need general relativity, because in Newtonian gravity there is no
Concept of
concept of gravitational waves or black holes and all that.
yeah.
So this
So
was the
the other
basic.
thing we can have. I mean, I'm actually writing now. Maybe you can stop recording now.
Oh, did I stop recording? Oh wait, how to stop? Pause.